So what we have seen last time using Simulink, using simulations, was something that qualitatively could be summarized in this way. We were considering a linear first order model, and the linear first order model was described by these equations: x dot equal to ax plus bu, and y was equal to cx plus du. And all these quantities here, a, b, c, and d, they were scalars, so they were defining this box that is our model. And what we did was to inject as input u a sinusoidal function. It was a sine, it was simply a sine, and then what we were doing, we were observing the output y. So the output y, we saw it was a sinusoidal function, but the interesting thing is that if the input is a sine wave or a cosine wave, there is really no difference. If the input is a sine wave, the output is a sine wave, or looks very similar to a sine wave, with amplitude that is different according to the frequency of the input. This is what I'd say is the most important property from a qualitative perspective of what we saw last time. So we were injecting a sinusoidal input with a certain frequency omega, and what we were observing was another output. Still, we don't know if it is the same frequency or not. We'll answer these quantitative questions today. But we were seeing another sinusoid, and this amplitude, since we changed the frequency, giving it different values, the amplitude of the output was changing according to the frequency. So can we somehow quantify this? This was just a qualitative, very qualitative analysis that we did just by doing some numerical experiments. So what we are going to do now is let's try to quantify this phenomenon. To quantify this phenomenon, we simply proceed as follows. Consider a linear first order system. Let's consider x dot equal to ax plus bu and y equal to cx plus du. All the quantities here are just scalar to make everything simple. And now assume an input of the form u of t equal to cosine of omega t. It's true, in our simulations we used sine, but cosine is going to make the computations just a little easier. So instead of using a sine, we'll use a cosine. Then we'll redo some simulations with a cosine just to verify that our quantitative analysis is correct, and also to verify that the fact that we're using a cosine function instead of a sine function actually is not changing anything. It's just shifting everything by a phase. So assume an input of this form, so now we can compute y of t. The output y of t is of the form. And now we can apply our formula, the variation of constants, to x, and then to apply to y, or we can apply it directly to y. So if we compute the formula directly on y of t, making the assumption that the initial condition is 0, so with initial state x of 0 equal to 0, so with this initial state, our y of t is going to be given only by the forced response, that is given by the integral from 0 to t of the exponential of a t minus tau b u of tau, that is cosine of omega tau, in d tau multiplied by a c plus d cosine of omega t. Okay, so this is the forced response and the output. Okay, for our analysis, let's assume momentarily that d is equal to 0. Assume for simplicity that d is equal to 0. What happens if d is not equal to 0? Well, all the computations that we are going to do now, they are still valid. Just remember to add d cosine omega t to what you have been writing. So just for simplicity, we'll do our analysis considering d equal to 0. So in this slightly simplified scenario, y of t looks like this. Integral between, well, there is a c, integral between 0 and t of exponential of a t minus tau b cosine of omega tau in d tau. So this is our output, and now we simply need to solve this integral for the specific input cosine of omega tau in this convolution integral. Once we have solved this, we have an expression for y of t that is explicit. So let's massage this expression a little better. So we can write that this is given by c. We can take the exponential of at, this part here, can be taken out of the integral because it does not depend on tau. Our integration variable is tau, so everything that does not depend on tau is a constant with respect to tau, and so we can take it out. It doesn't matter that exponential of a of t is a function of t as one of the extremes of the integral. This doesn't matter. Exponential of at does not depend on tau, so it gets out. Same happens for b, and so we are left with something that is a little more easy to deal with. That is the exponential of minus a tau cosine of omega tau in d tau. And now this is an integral that typically in every calculus class we learn how to deal with it. Now I don't think that this is a class where we should be too concerned about knowing how to do integrals. You should already know, so that's not what this class is for. So we are going to use some software, and it's also a good way for me to introduce you to a software that I like a lot. It's a software for symbolic computations. So if I want to compute this integral here, I can do that by hand, as I was taught in calculus, or I can use some good software. And in this case, I'm going to use software that is called Maxima. I use a special interface for Maxima because actually Maxima is a command line software. I like this interface, so I use WX Maxima. So what do? I simply write this integral. I write the expression e, when you are considering Euler's number, E in a maxima you use the percentage before E, so that maxima knows that this is Euler's number. So E to the exponential of minus a tau, so exponential of minus a times tau, and we multiply this this is multiplied by cosine. Instead of omega I use W because W looks a bit like an omega, so I don't have to do to type too much. And this is the expression the maxima has seen. I go here into calculus, integrate, and now I take, if I use the percentage here, means that I want to integrate the last expression that I have entered. The variable that I want to consider for my integration here is tau, and that's all I have to do. Integrate the previous expression with respect to tau, and I get this. Now this quantity here needs to be computed in t, and then we have to subtract the same quantity with tau equal to 0. So let's write this quantity here, and I replace tau with t, so I have exponential of minus a t that multiplies omega sine of omega tau, omega sine of omega tau, divided by a square plus omega square. So this is the quantity that maxima has given to me as a function of tau, with tau replaced by t. Now the same quantity when tau is replaced by 0. So let's see what we have here. The exponential of 0 becomes 1. Sine of 0, when tau is 0, omega tau is 0, the sine is 0, so the sign disappears. And we are only left with a cosine of 0, that is 1, and the denominator stays the same because it doesn't depend on tau. So when I replace tau with 0, what I'm going to get is the following quantity. That is minus, so plus a divided by a square plus omega square. So if everything is oh, I forgot I didn't finish the first expression. The first expression has an omega sine of omega tau, but also has minus a cosine of omega tau. So this is the first expression with and here we have t, and here we of course we have t. So sorry for the little mess up. If I replace this expression, if I replacing this expression tau with t, I get this expression here. And if I replace in the same expression tau with 0, I'm left with exponential of 0, so 1, and I have minus a, but I have to subtract it, so hence plus a square plus omega square. So this is what my expression looks like now. So let's do a little better. Let's see how this. Let's massage this a little more. So let's consider this simple term. I'm taking this term and I'm multiplying this by CB exponential of AT. So I have a CB divided by a square plus omega square exponential of AT. And this is the first term. And the other term is going to be CB exponential of AT cancels exponential of minus AT. So I'm only left with omega sine of omega t minus a cosine of omega t divided by the usual denominator, that is a square plus omega square. Okay, so let's save this real quick. Let's go, let's create a new page so that we can proceed with our computations. So this is the expression that we have so far. This expression is correct, or at least I strongly believe it is correct, unless I have made some minor mistakes, but it has a term that has an exponential of at and a constant. Once we fixed omega, this quantity multiplying the exponential of at is a constant, and then we have another term that is, roughly speaking, a constant times a sine and a constant times a cosine. So a first observation, this term, if assuming that we are not in the trivial case where either c or b are different from 0, if a is a positive quantity, then we have this exponential of at that is going to diverge. So whatever this quantity that multiply these sines and cosines are doing, they become negligible compared to the exponential of at. And if a is greater than 0, we already know that the system is not going to be stable. So what I'm saying is, let's put ourselves in a condition where we know that the system is Beeble stable. So let's consider a case where the system is Beeble stable. And the reason is that if the system is not Beeble stable, if we are putting a sinusoidal input, the output is going to diverge most likely, and so it makes no sense to consider the frequency of the sinusoidal output, because it's not going to be sinusoidal. It's going to be completely dominated by this term here. So the case where the system is Beeble stable is given by c times b needs to be different from 0, and the a needs to be less than 0. This guarantees Beeble stability. We have seen that actually it's an if and only if. The system is going to be Beeble stable if and only if these conditions are verified. So under this condition, under Beeble stability, we have that y of t is the superposition of two terms. The first term is given by this exponential that is going to 0. If a is strictly less than 0, this exponential decays exponentially, and so after some time becomes negligible. And what is left is only this part that is periodic. So we have y of t that is given by, and now we can take this part here, and also I take the rest. This part here is goes to 0, so it's transient, and goes to 0 when t approaches infinity. And instead, this is a steady state response, and because our input is periodic, and this is not so surprising that it is periodic. This is also periodic. It's also more than periodic. We are going to see that this is a sinusoidal function as well. Okay, but this is under the assumption we were saying that our parameter a is strictly negative, and considering c and b that are different from 0. If either c or b is equal to 0, the output is 0, so that's we immediately get the result, so that's a very, very trivial case. So what we are going to do is we are going to work on the on this part here, on the part that we have on the right hand side, on the steady state part. We are going to have the full response with the transient and the steady state, but we are going to rewrite the steady state response in such a way that we can analyze it better. So what I'm going to do is the following. I simply rewrite the part that I know is going to 0 without touching it, because after all it goes to 0, so there is no reason to put any effort in making this look like any better. Instead, for this we can do something better. We can write this in the following way. I write this as CB, and I have this denominator. A is a parameter. We said that it's negative, but a square is positive, plus omega square. Omega is a frequency. Typically we interpret that as a positive number, but even if it was a negative number, we square it, so it's still positive. So this denominator is positive. I take its square root and I write it here. So what I'm left with is with this quantity, and now I reorder the terms. I prefer to write first the term with a cosine. So I have minus a divided by a square plus omega square, square root, because I took the square root here, so I'm left with another square root. And then I have the other term that is instead, and I forgot, of course, cosine of omega t. And then I have the other term that is given by plus omega divided by square root of a square plus omega square, and this term is multiplied by sine of omega t. Now, why did I do this? I did this because I'm trying to write this steady state solution as a single sinusoidal function. Now I have cosine plus sine. I don't like this. I'd like to write this as a cosine of omega t, and we'll see that what's going to happen is I have to introduce a phase shift in the argument of the cosine to take into account the sine. So let's see what's happening here. We have a quantity here that is minus a divided by the square root, and another quantity here that is omega divided by the same square root. If I take this quantity with a denominator equal to minus a and I square it, and I take the second quantity with denominator omega and I square it, I have that the sum of these two squares is equal to 1. So what I'd like to do is to interpret this quantity here on the left as a cosine of an angle, this quantity here on the right as a sine of an angle, so that I can write my this expression as I can use some trigonometric identities so that I can put all these cosines and sines together into a single sine. In particular, what I want to use is, I'll put here a reminder, or refresh of trigonometric identities. I have always hated all these identities, but they happen actually to be useful. So I don't know if you remember. If you don't, you'll remember in a second, and you'll have to remember. The sine of the sum of two angles, alpha and beta, can be written as the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. Okay, this is one of the two more often used trigonometric identities. The other involves the cosine of the sum of angles, and this is actually the second one that I'm writing right now is what I think is going to be more useful here. If you have the cosine of a sum, that's equal to cosine of alpha, cosine of beta, minus sine of alpha sine of beta. Okay, so given this quick refresh, let's see what we have here. Well, I'd like this to be my alpha. This is my alpha. And I like this to be, since I want to write this as cosine of alpha plus beta, I'd like this to be minus sine of beta. And I'd like this to be my cosine of beta. That's what I'd like. What I'd like to write. So let's simply proceed. These are two quantities, and let's see if we can make some observations about these functions here. Let's start with this minus a divided by the square root of a squared plus omega squared. So here I put on the x-axis omega, and here I put minus a divided by the square root of a squared plus omega squared. And I want to plot this for different values of omega. So let's start when omega is equal to 0. Remember that a is a negative quantity, so minus a is positive. The square root is always positive, and so when I take omega equal to 0, I have that this is equal to 1. Now what I do is I make omega grow a little and more, and so the numerator stays the same, the denominator starts growing, and when omega goes to infinity, this quantity approaches 0. So what I'm saying is that if I draw the function, and you can do the whole study of the function if you want, but the behavior is going to be monotonic and something of this sort. Okay, so this is my cosine of beta, and actually I can give it a better name if I want, because I'm going to call this cosine of phi. Okay, so this is going to be my cosine of phi, and this is my sine of phi, because I prefer to call it phi. That's what's going to be its name. So this is somehow a quantity that when omega changes from 0 to infinity behaves like this, and the same can be done for this other quantity as well. We can compute what this quantity looks like for omega equal to 0, and then we can make omega go to infinity and so on. How much is going to be this angle phi? Well, as the important thing, and that's why I drew the cosine. So the observation that I want to have here is that cosine of phi is always non-negative, because a is strictly less than 0. That's what we had. So under this assumption, if the cosine is always non-negative, we have that our phi is given by the arctan of if this is our minus sign, this is our cosine, and since the cosine is positive, I can compute this by taking the arctan of, and I now need to take the tangent of phi, so tangent of phi, that is equal to the arctan of I take this quantity here, but the tangent of phi is sine divided by cosine. Here I want this to be minus sine because the formula here requires a minus, so I want this to be a minus sine. So I'll have to put a minus there. So this is given by minus omega. Well, let's write everything. Sine of phi divided by cosine of phi equal to arctan of, and now I take this quantity but with a minus, so omega divided by the square root of a square plus omega square divided by, and remember the minus a that divides the square root of a square plus omega square. So this is equal to the arctan of omega divided by a. So what I'm saying after this, I'm saying that if I take this angle phi to be the arctan of omega divided by a, this quantity omega divided by the square root can be interpreted as minus the sine of phi. This other quantity, minus a divided by the square root of a square plus omega square, is the cosine of this angle that I have just found. So under this definition, we get defining phi as the arctan of omega divided by a, we can now write y of t equal to, and now we take this part that is transient, ACB divided by a square plus omega square exponential of at. Remember, a is negative, so that's that doesn't give us any problems because this decays as an exponential, and then we are left with CB divided by the square root of a square plus omega square that multiplies, and now we can apply our formula, our trigonometric identity. So we have, this becomes cosine of alpha plus beta, where alpha is omega t and beta is this angle phi. So this becomes times cosine of omega t plus phi. So that's what I want you to learn from what we have done so far. If a first order Bibo stable linear system is forced by an input u of t equal to cosine of omega t, the output y of t is the superposition of a transient term going to 0 when t goes to infinity, and a steady state term which is sinusoidal with the same frequency of the input, with the same frequency of the input. Why? Because here we have omega, so we force this with a simple cosine of omega t. Now we got something that is a little more complicated, but it has still the same frequency of the input, and that's okay. What about the amplitude? Amplitude equal to, let's see what the amplitude looks like. This is a cosine, and the amplitude, instead of going between -1 and +1, so the amplitude is not 1 anymore, is going to be equal to CB divided by square root of a square plus omega square. If you remember, in our simulations we were seeing that the higher the frequency, the smaller the amplitude of the output was, even though we kept constant. We kept the amplitude of the input constant. So we are injecting the same sinusoidal input with the same amplitude equal to 1, and we were observing that if the frequency was getting higher and higher, the amplitude was getting smaller and smaller. We see this, and now we have a complete quantitative characterization of this behavior. The amplitude is going to be C times B divided by the square root of a square plus omega square. You make this omega bigger and you're going to see a smaller amplitude. Not only, there's something that I didn't want you to pay attention at the moment, because maybe it would have been too much detail. The output and the input are sinusoidal, same frequency, but they are not in sync, in the sense that their peaks are not aligned. There is a change in phase. This is called phase shift, and that's how we are going to call it. A phase shift phi that is equal to, and we have computed here, equal to arctan of omega divided by A. Remember, omega is positive, but A is a negative quantity. So let's take a look at what the arctan function looks like. If you consider a generic angle alpha, and here you plot arctan of alpha, that's what your arctan function is going to look like, if you remember it from calculus. This quantity is given by pi divided by 2, and this other quantity here is going to be minus pi divided by 2. Since A is strictly negative, omega is positive, then what you're going to see here in the specific case is that your phase shift is always going to be negative. So that's where we are here. Since A is negative, the phase shift in this case is negative 2. It's not always going to be the case that the phase shift is going to be negative, and it's not going to always to be the case that the amplitude gets smaller and smaller if you increase the frequency. We are going to see this very clearly with second order systems. In the case of first order systems, yeah, that's actually true. We have that this amplitude here is going to be smaller and smaller. Okay, so this is a full quantitative characterization of what happens if you inject a sinusoidal input into a first order linear bounded input, bounded output system. So you know exactly, we know exactly now what we are going to get.